This is the first video in the topic on equilibria. Equilibria is really important to us as chemists. It's so important. You've already studied a little bit of this at GCSE. We're doing it again in year 12 and we'll return to it in year 13. The point of what we're doing now really is to recap the year 11 work, the GCSE work, and take it a little bit further. Next year, we treat this more mathematically. Now, when you did this at GCSE, I imagine you didn't really enjoy it very much. It's quite an abstract topic. It's something which is quite tricky to get your head around, and it's done quite quickly. So the point of revisiting it is to just consolidate that work and take it a little bit further by introducing a new idea called Kc, the equilibrium constant. That prepares that groundwork ready for the mathematical treatment which comes in year 13. Okay, let's go back to what you did at GCSE and just clarify the key points that you should have learned. As you know, most reactions go to completion. The top one of these reactions, magnesium plus oxygen turning into magnesium oxide, is an example of that. I've got my reactants, A and B, in this case magnesium and oxygen, and they're turning into the product, magnesium oxide, or C. And generally speaking, that's what happens for most reactions. If I put some magnesium in some sulfuric acid, it'll turn to magnesium sulfate and hydrogen. At the end of this particular example, provided there's enough oxygen present, there will be no magnesium left. The reaction has gone to completion. What you were introduced to at GCSE, probably towards the end of year 11, was this idea of equilibrium or equilibria, where I can take my reactants, A and B, and they will form C, but C can turn back into A and B. Now, the confusion at GCSE is often this. People think you can get A and B, your reactants, and to turn them into C. And at some later date, it's possible to get C and turn it back into the reactants, A and B. It's more subtle than that. Those two processes happen at the same time. So in my example of nitrogen plus hydrogen turning into NH3, ammonia, when I first get my nitrogen and hydrogen, they're going to react together and they're going to start to make the ammonia. So you think about what's going on here. The nitrogen and hydrogen concentration starts to go down and the ammonia concentration starts to go up. But the moment that the ammonia is formed, a small percentage of that will be turning back into the reactants. So I've got the forward reaction and the reverse reaction happening at the same time. So when you learnt that this sign means reversible reaction, it's not necessarily telling you the full story. The two reactions are happening at the same time. Now clearly, when we first start this reaction, our concentration of reactants is going to be much greater than the concentration of products, which at the beginning will be 0. So the rate of the forward reaction will be a lot faster than the rate of the reverse reaction. But at some point in the future, at some point as the reaction progresses and the concentration of the products is going up and the concentration of the reactants is going down, the rates of those two reactions, the forward and the reverse, will become equal. They will become the same as each other. And that's the point that we're interested in. That's the point when equilibrium has been reached. We call it dynamic equilibrium. There are two words there, and there are two things that we need to understand. What do we mean by dynamic, and what do we mean by equilibrium? Well, dynamic is to do with movement. The reactants are turning into the products, and the products are turning back into the reactants. It's dynamic. The rate of the forward reaction is the same as the rate of the reverse reaction. Now, if that's true, if this stuff is turning into this stuff at the same rates as which the products are turning back into the reactants, the concentration of the reactants is clearly going to stay the same. It's not going to change. Similarly, the concentration of the products will remain constant. It won't change because the product is being formed at the same rate as which it is breaking down to turn back into the reactants. So here's the key points. Dynamic equilibrium is when two things are in place. The rate of the forward and the reverse reactions are the same. And the concentrations of reactants and products will stay constant over time. So the concentration of the reactants will stay the same. The concentration of the products will also stay constant. But it's important to recognise what we are not saying is that concentration of reactants is the same as the concentration of the products. We're not saying that at all. So we've got a balance. It's like a seesaw and it's not like a seesaw. That's an analogy which is often used, the seesaw analogy. Now, when you think of a seesaw, you think of it being balanced. You think of the things on one side being the same and balancing out the things on the other. Dynamic equilibrium is not really like that because you can have the seesaw in different positions. I could have a dynamic equilibrium where the concentration of reactants at equilibrium is really, really high, and the concentration of the products is really, really low. Now, what I might want to do as a chemist or as a chemical engineer is design a process where I can change that position of equilibrium so that I increase the concentration of products and decrease the concentration of reactants. And I do that by changing things like concentration, pressure, temperature. Okay. I'm going to introduce you to a new idea, the equilibrium constant. What on earth do we mean by the equilibrium constant? Well, let's go back to a very, very basic equilibrium. What we're saying for Kc, the equilibrium constant, the Kc is a ratio. It's a ratio telling me about the concentration of products to the concentration of reactants. The square brackets mean concentration of. So I'm interested in the ratio, the concentration of products divided by the concentration of reactants. So in this case, what I would be writing would be the concentration of the products, C, divided by the concentration of products, A and B. If I were to know the concentration of each of those terms, A, B and C, I would be able to generate a numerical value for Kc. And the size of that numerical value tells me something about the position of equilibrium. Does it lie to the right-hand side in favour of the products, or does it lie to the left-hand side in favour of the reactants? And am I able to change the value of Kc by changing conditions? That's something that we're going to look at as we move through year 13. Does Kc have units? Well, possibly. If you think about concentration, concentration is measured in moles per decimetre cubed. So let's think about the units. C is measured in moles per decimetre cubed. A is also measured in moles per decimetre cubed. B is also measured in moles per decimetre cubed. So Kc does, in this case, have units. If I were to simplify this expression, I've got a moles on the top, and that will cancel with one of the moles on the bottom. I've got a dm to the minus 3 on the top, and I've got a dm to the minus 3 on the bottom. Now, if I cancel everything out on the top, that's going to leave behind effectively a 1. So what I have got in terms of units here is 1 divided by moles per decimetre cubed. Not crazy about that. It'd be nicer if I had all of these units on the top line. I can do that, and it's really simple to do. All I have to do is change the indices, the power, on each of the units. To bring moles to the top, I'm going to change the power. To bring dm to the minus 3 to the top, I'm going to change the sign of the indices. So all you had to do was change the sign of the powers to bring them to the top. So that's a very brief introduction about Kc. Now clearly, if I were to have other products, that would change the units. So Kc does not have units which remain the same all the time. Each reaction has to have units which you need to calculate. And it's possible that Kc will have no units at all.